Now let us study about induced electric field outside a cylindrical region time varying magnetic field. To understand the situation, let's have a look on this picture. Here we are given with a long solenoid in which a current I is flowing, which produces a magnetic induction B along the axis of the solenoid. And outside the solenoid there is a coil along with a galvanometer, and here if this current increases with the time, then this magnetic field will also increase with time, and on changing this magnetic field we can see the flux passing through the outer coil is also changing, due to which we can say the galvanometer will be deflected as a current is induced in the outer coil. That means in this outer coil, if magnetic flux in this direction is increasing, this will have a tendency to induce a current in anti-clockwise manner so as to oppose the increase in this magnetic field, and the galvanometer will deflect on the left hand side. So we can say this induced current in the outer coil is also induced by some electric field at this point. So we can say whenever in a region magnetic field is changing, outside the magnetic field also tangential to the coil or a circular path which is symmetric with respect to the cylindrical region, an electric field is induced. And again the line of forces of this electric field will be circular. And let's have a look on the situation in a different way. Like if we just have a look on the cross section of this, it will look like this picture. In this picture you can see we have drawn this as a cross section of solenoid in which magnetic induction is in inward direction, which is of radius r, and at a distance x outside we consider a circular path. We have removed this outer coil and we consider a path, and as magnetic field is increasing in inward direction, an anti-clockwise electric field must be induced over here, of which the direction at every point will be tangential to this circular path. And if there exists a coil, this electric field will give rise to an induced current in the coil. Now in this situation we can directly state for outer points, that is for x greater than r, here we can use the total EMF induced by Faraday's law. We can write is given as pi r square dV by dt, and it will always remain constant no matter how large the path is, because no matter how far you will move away from the center, total flux will remain same, and it must be equals to integration of E dot dl for the closed path outside the field. So it will be integrated from 2 pi x, 0 to 2 pi x. So in this situation we are getting as symmetrically we can say E is uniform, E can be taken out, integration of dl from 0 to 2 pi x will be equals to pi r square dV by dt, and further we can write it as E into 2 pi x, which is equals to pi r square dV by dt, and in this situation pi gets cancelled out, and the magnitude of electric field we are getting is half r square by x dV by dt. That means in this situation you can see the magnitude of electric field decreases as we move away from the center. So in previous section we have studied about the orientation or configuration of electric lines inside, and we have seen as we move away from center inside the density of electric lines increases. But in this situation outside points, here we can see for x greater than r, for outside points electric field is decreasing with x. So here we can say as we move away, the density of electric lines will start decreasing, or we can say the line separation will increase as we move away from the center outside the cylindrical region. So be careful about the magnitude as well as the orientation of electric lines in the outside region.